Welcome back, everyone, to another episode in the CrySP speaker series on privacy. Today we have Breaking the Web is Good for Privacy, presented by Eric Jollès. Eric Jollès is a doctoral student at EPFL, working broadly on network security and privacy topics. He's advised by Carmela Troncoso in the Spring Lab, where he designs and attacks existing systems to create new solutions that make the internet a more private place. He holds a joint master's in cybersecurity from EPFL and ETH Zurich. The talk is going to commence, but for anyone who is joining us remotely, you're able to type questions in the chat and we'll have them read out to the speaker. With that being said, Eric, please take it away.
Thank you for the kind introduction. So yeah, I'm a third-year student at the Spring Lab at EPFL, and today I'm very happy to share with you the latest research I was doing about breaking the web. And we showed that can be good for privacy if you do it in a smart way. And yeah, it will be really focused on website fingerprinting because it's a topic I'm doing in my research. Just a quick note about my lab, so the Spring Lab. So it's supervised by Prof. Troncoso. It's now at EPFL, and it was moved out to Max Planck Institute in Germany. And our main focuses are machine learning in general, what their impact on society for security, privacy, and fairness. We also do some engineering in privacy preserving systems and framework for privacy evaluation. And I just bold the topics I'm mostly doing in the lab, so everything related to network security and privacy. So this will be the threat model for today. So here we will have always Alice that want to communicate or browse a website. So it can be example.com. And in this scenario, even if the traffic is encrypted, everyone between Alice and example.com, so it can be her boss, intelligence agencies, ISP, or just anyone curious, can see the IP header of the traffic. And it often contains the IP header and of the source and the destination IP. And then an adversary that sits in the link can just see that Alice did browse a certain website. And this is what an adversary can do when someone does not trust such system. Someone can use anonymous communication networks, so it should hide the header of the traffic. But still, an adversary that sits between Alice and the anonymous communication network can still see the packet timing, packet sizes, and packet direction. And with these patterns, the adversary can train a machine learning model and predict the websites that Alice browsed. So at the end, the adversary will still be able to know that Alice visited example.com. So what can we do to make defenses on this field? So what you can do is to add dummy traffic to your network. You can also add delay. So for example, you can say, I will send a packet every second or just any random of time to try to kill the timing patterns. And a new kind of anonymous communication network that's now newly implemented as mixed nets that uses both in a certain way. And I will introduce you the topic with an anonymous network, mixed net called NIM, that is used since sometimes now. And just to introduce you what can website fingerprinting pattern, if they can still survive in mixed net defenses. So this is some work that we published at PETS this year. So it was done with my colleagues from NIM and my Prof. Carmela Troncoso. So NIM is a mixed net. So it was firstly designed to send packets, like just messages packets, so Signal or just Bitcoin exchanges. And they also implemented it so you can access the web. So for this, Alice will communicate with a proxy. The proxy will send all the packets of Alice to the mixed net. So it will go through 3 different mixed nodes. It will reach the requester, and then the requester will relay the HTTP request and the responses from the web server. And to hide the traffic patterns on this, NIM is implementing 4 different mechanisms. And yeah, this is what I will quickly introduce because they will be important to understand how they impact the network fingerprint of the communication. So first mechanism is called mixing delay. So every time a packet enters the proxy, it will go through the mixnet, so through 3 mix nodes. And at every mix node, the packet will be delayed for a random amount of time. So by default, it's around 50 milliseconds. And this amount of time is defined by Alice. And the goal of this mechanism is to break input-output timing correlation. So if an adversary sees a packet coming out of mix node, it cannot correlate to the one that was coming in because there will be some random delay, and with enough packets, it will just not be enough to make this correlation. The second mechanism is called loop cover traffic. So in the background, Alice will send some packet that will go into the mixnet and go back to her. Yeah. These packets will be spaced in time, so there will be some random delay, also defined by Alice. It's approximately around 200 milliseconds by default, and this will create background noises, so it will hide the activity of Alice just by with this noise. The third mechanism, so when Alice wants to send real packets, so HTTP queries, HTTP posts, or stuff like this, she will send them at a steady rate, so also like before, separated by time, by default 20 milliseconds. And when she does not have any real packet to send, she will send loop cover traffic instead. So the kind of packet we just see before to add some noise. And this has then 2 consequences. So it hides the timing pattern of the real activity because you just add random time between the packets. And since you add also packets when you don't have real packets to send, it will hide when Alice has something to send or not. So really, it will hide her traffic. So this was when the packet goes from Alice to the website, but the other way around, you can also have such a rate, so such a defense. So it will go from the requester back to Alice. But by default, it's disabled because it's expensive to keep one connection for every user from the requester side. So NIM deployment team decided to not use it by default, and we'll see that's kind of the weaknesses of the system. So with these 4 mechanisms, we have multiple research questions. Do NIM's 4 mechanisms actually stop website fingerprinting? Which mechanisms are beneficial? Which are detrimental? We'll see there are some. And can we build stronger defenses without modifying NIM's mixnet? So that will be what we can do. And how we measure it. So we have isolated 6-node testnets. So we are not using the real NIM mainnet. There are multiple reasons of that. It's also because back in the days, it was very not stable, and we just wanted to see how the protocol behave on the network. So this will really be considered as a worst case for the defender because there will be no added noise or like machines that dysfunction. So it's really to see how it behaves in lab conditions. We are browsing real web pages with Firefox and Selenium over the big enough URL list in closed and open world settings. We will mostly see closed world setting today. So it's when you have classification and you just want to know among this website, which one was browsed by Alice. And just as a note, we use state-of-the-art attacks. So TikTok, which is used in most of the papers nowadays. And yeah, we use the F1 score. So 1 is considered as perfect classification and 0 is considered as the defense worked really well because you cannot make any guess what's going on. Okay, so to understand if some traffic is fingerprintable, a good way is to plot the packet count per timestamp, so per second. So here it's the packet count per 50 milliseconds time windows. And here, when we see the packets going, like the packets in general going from Alice to the proxy, it's where the attacker sits, we can see there is no really patterns. It looks quite random. You cannot say when there is connection, when there is not, and yeah, how many packets is sent. And this just shows that defense provided by the client Poisson rate really is efficient. However, the other way around is another story. So as I said, by default, the requester does not send at a specific rate packet back to Alice. So the packet will come as they arrive into the mixnet. So if you have a burst of traffic like this, if you add some random delay, you will have a burst that will be shifted and spread out, but this burst will remain consistent throughout the different browsing session. So will still be a fingerprint for the website. And this is what the number also show. We have for NIM, F1 score, the experiment we just saw before, F1 score of 0.87, which is quite high. So if you compare tutor, it's 0.08 in the same lab settings, but it adds a lot of overhead and with bandwidth, because every time you will send packets that just are dummy, so it adds a lot. And it's still not very efficient if you compare it to other Tor defenses. The impact of the mixing delay, as we saw, is not that helpful for hiding the fingerprint, because so it shifts and spread it out. But still, we have a high F1 score. And our second question was, does the mixing delay have an impact or not? And what we noticed by removing cover traffic, so just keeping the mixing delay, is that this mechanism is even detrimental for the defender. So on the left side, you have a small mixing delay, so around, so it's 0 milliseconds, so no mixing delay. On the right side, you have 100 milliseconds, which is double of what is done by default on NIM. And what we can see on the right side is like the bursts are more separated. And this separation makes them more identifiable by the machine learning model. And when you have higher mixing delay, you have F1 score that is higher, so the defense is less effective. So when you have mixing delay, basically you're not defending as great as when you don't have. So it's quite detrimental. So if we cannot have any improvement with the mixing delay, perhaps we should turn on what's called the requester Poisson rate, so the rate that comes from the requester to Alice.
No question.
Yeah.
Does the loop traffic not interfere with the web traffic signal? Oh,
yeah, that's the problem. It's that the packet should arrive to Alice. And actually with the implementation, you have loop cover traffic that never reach Alice. So all the packets the requester will send, and it will be a burst of packets, like just you will be able to see when you have something coming to Alice. So it will not look like a big burst like before, but you will just see that you will have more packets, like double as usual. And just to have the time of the burst, so like at this point, I have double the amount of packets, then 2 seconds later, double, you still can learn what's going on. Like the F1 score dropped a little bit, but not as much as it should, because it also adds a lot of overhead on the latency and bandwidth. So it's still not a good solution. And this is how we arrive to what should be the defenses for NIM. So basically, the loop cover traffic should not be loop cover traffic, it should arrive to Alice. And this is what we did with Poisson. So Poisson will be this, but we just activate the cover traffic to Alice when Alice is browsing, because otherwise it's just too expensive. And so F1 score is very low. but still it adds a lot of latency and bandwidth overhead compared to NIM. So that's on top of NIM, so it's very expensive. And so we also wanted to try to see what's happening if we are using more standard defenses for NIM. So we use different defenses. We use front and WTF-pad. They both don't work out of the box because, as you can see in blue here, NIM is really full of noise when there is no real communication. So you need to learn from this in these defenses, and the noise does not make it easy. So what we did, we just adapted the WTF-pad to NIM. So we take the same ideas, and this has two advantages. When we implement it, we have no latency overhead because we just hide the traffic when there is some, and we have very low bandwidth overhead. So just that you see here in orange is what we had as flake burst in an example. And yeah, so lower F1 score, but still like some overhead, but we are getting in the right direction. And it will be implemented this year by NIM. So yeah, they will more implement the basics of these defenses, and then we'll be able to build new ones on top of it to make browsing safe. So yeah, like the biggest takeaway of this, it's like NIM messaging defenses don't fully transfer to web browsing. And there we go to the second part of the talk is like, we saw that there is a big burst and that this burst is hard to defend. And then our idea is, can Alice modify the burst at the application layer? So application layer will be more at the HTTP layer where you can like do requests and like just apply some time between them, for example. And this is exactly what Cherubin Giovanni did in his paper, Yama. So here, how the defense works. Alice, we send HTTP request to the defense, and the defense will delay, reorder, and inject fake requests to them. So as you can see on the right side, the requests will look different. They will be reordered, some will not, and you will have some fake requests going on. But it adds a lot of bandwidth and overhead by design because yeah, you're just delaying and injecting some packets. And it could work back in the days when the web was quite simple. So here you can see CNN.com, you have one image, not that much text, and yeah, so not that much resources to load, and then not that much packets. But web pages did evolve a lot these last years, and this is how it looks like 2026. So it's really more now web applications. So on this, you can see a lot of different images. You had also some videos, you have advertisements, you have a lot of scripts that happen in the background and you don't really know what they are doing. So yeah, it's really evolving, and such defenses as Yama is not quite usable anymore. And as I said, like a lot of new resources, and then it will create for each resources some packets. And these packets, even if they go through anonymous communication network, they will still be identifiable because they are quite unique. And so in the research area, we often try to understand how to hide web pages that generate large and complex payloads. And we often go to a trilemma called anonymity trilemma. And this trilemma states that you cannot have high anonymity, low latency, and low bandwidth at the same time. So just to try to make you understand how it goes, so you can have low bandwidth and high anonymity. For example, if you add delay, so latency will be high because you add some latency, but you will not add additional packets, so latent bandwidth will still stay low. And if you just have one packet every second, you can still have high anonymity. You can have high anonymity, a low latency if you're just adding a lot of dummy packets on top of what's going on. So bandwidth will be impacted because you have packets, but at the same time, you will not add any latency. And if you send, for example, at your maximum bandwidth, some packets will never be able to know what's happening or not. And you can have latency and bandwidth, so low latency and no bandwidth, but then like no anonymity. So it's not really something we want to see today. So this will be considered as just browsing the normal web. But all of these statements were made with the idea that you cannot touch the web page that entered the system. And our idea is that perhaps if we load just fewer elements on the page that the user think it's useful or like want to browse, we can make the fingerprint smaller, so have less packets, and with less packets, you will it will be more easy to hide the traffic. This was already done in a way by the Tor browser. So here the goal was to really limit the number of JavaScript on sites. You had also fonts, icons, MySable, and images that were disabled. And you can click to play for certain content, so audio, video, and WebGL. It just provides guarantees to simple page, but as we saw with previous pages, that they are becoming more and more complex. But how does it work with complex pages? It does not work pretty well. And this is for this reason, is that the web is now full of different components, and every component has a specific purpose. So you have article for a journalistic task, for example, you have comments, advertisements, search for videos, other components. And you also have in the background some analytic scripts, tracker scripts, and fonts. And when a user has a specific purpose, for example, read an article, perhaps it will not need to load every other component. So here is just that to show you that if we don't load the ad, for example, don't load the images, perhaps if Alice just wants to search for the news about Artemis mission that will be somewhere else, she will still be able to do it because the search bar will still be available and she can still browse the newspaper website. But now what happens if we remove the search bar? Probably she will not be able to look for her paper anymore. And this is exactly what our project is about, is that depending on the purpose of different users, you can browse internet still by loading just the content you want, but it will imply that you will not be able to do other things, and that that's breakage, as we call, is relative to what you wanted to do before. So yeah, so this is the second work I want to speak about. This is done with my colleague Said and my Prof. Troncoso. So how does it work? So first, you want to go to a URL. You will load the index.html document, which is the basic page where you will have all the resources that you will need to load. So it will give you the resources you want to load. And then you will have a filter that is LLM-based in our implementation. So you will feed to this resource filter the web resources, the index.html document, so how the page looks like, and the purpose of your browsing session. It will block some resources, the filter, if it does not consider them as useful. And if they consider them as useful, it will allow them. When you allow new resources, you would have a new page state. So you can, for example, load certain images or components of the website. And also you will have new resources to load because, for example, JavaScript contains certain resources that still will be needed to load. And then you just enter in the loop where you will loop until you don't have any resource to load anymore. So from this, we have three main questions: is how to express the purpose. So it will be fine-grained or not. That's what we'll see later. The second question is how to distinguish resources. So that's more an engineering task. So how to build the resource filter. As I said, it will be LLM based. I'll also show you this in a second. And finally, does it work? Can we see, can the real user benefit from it? So the first question is about purposes. For example, if you go to Airbnb, perhaps you just want to just book a place where you already know where it is. So it will be the first option. So probably you will just want to have this little bar. And another purpose could be to discover interesting gateway deals. So like perhaps more browse in this web page. But still, like purpose looks quite similar, but probably we'll need to have to load different components in the web page. And it will be kind of the same in different web pages. So for example, should the purpose when you want to write a post on LinkedIn or just make customer reviews, should the purpose be the same? Should it be publish a post, write a review, or just in this case, like fill a form? So this is a big part of our research is try to define this. And this is quite complex because purpose is, not very, it's very hard to define precisely. And it can be very different way we can define it. So the most easy way would be to ask the user to say what he wants to do in a specific web page. So it will be user defined. But like for large scale experiments can be quite hard to deal with that. What we are doing in our experiments is more about this. So we inferred from the website browse what is the purpose. So for example, if you go to Wikipedia, probably the purpose on a specific page will be just to read the article. This is what we are doing in our experiments to test if our system is working. And finally, we could think about doing something more global, like just ask the filter to say, okay, just eliminate all the useless scripts, for example, like can be like, I don't want advertisement tracking and analytics components. So we could also think about that. But yeah, as I said, we decided to go this way for our experiments and just to show that the system is working. And to be able to have like a broad number of tasks that are varied, we had to go through the web browsing literature, and we found that a task can be defined as objects merged with actions. So for example, I will just quickly show information times consume will be, for example, read article, or like create times social will be to write a blog post. And we are just using this to be able to have a wide number of experiments to be sure that our system is working on all of these different scenarios. So now we express what is a purpose, and the interesting thing will be to know how to distinguish resources. So imagine that you want to find an hotel in Calgary. So I was there last week, and to be honest, it's quite a mess to find some. And so if you want to go to do that, the filter will receive as input some URL like this and URL like this. And it's quite hard to know what's really useful. Here on the right side, you can see it's probably will ask for an icon. So you can probably think that it will not be very useful. However, on the left, it will be more thumbnails for Calgary, probably. So probably you will need to load that. But that can become harder because URLs are not always descriptive. So for example, between these two, it will be quite hard to know what to load just by looking at it. And the problem is that just with the URL is not enough, but if you take the URL and want to understand how they look like in the index.html, it's nowadays quite hard. So what we do in our prototype is to extract the page state of the index.html. This page state, it will be with multiple components. And then we will link all the components to all the resources to their components. I will quickly go through how it works. So you have, this is the index.html. You give the page state info. You have the AX tree, which is on the browser nowadays some description of the current web page that you can have by querying the browser. We give it to a semantic tree that will extract from this AX tree the components, as said before, and it will give a region tree. And then the region tree up, you put it together with the request, and it goes through the resource tree. And then with an LLM that knows nothing else than the prompt that we give it. So like, do this task for this purpose with this index.html, with this resource tree. So we just give that, and it will say if the resource should be allowed or blocked. And yeah, and then we have like some implementation issue, like how to enter resources the filter is unsure about, because as we saw before, for this two, for example, it can still be tricky to understand what should be loaded or not. So the first answer we have to that is to block by default every resources that we are not sure about. That has good, that has some advantages. So for example, you will not load a lot of resources, so the fingerprint will be smaller. But at the same time, yeah, it will often break the page. If you allow all of them by default, this is when you will have the lowest breakage, but at the same time, yeah, you will still load a lot of resources. And the third way we could do it is to just ask the user, as our browser did it, but yeah, just click to load. But yeah, it was done with our browser, and it's quite hard to do it for user studies. So in our experiments, we are mostly using between block by default and allow by default to see the difference. And now the last question we have is, does this thing work? So yeah, to show it, we did an experiment on YouTube. So the purpose was just to watch this video. And as you can see, if you just want to watch this video, you will just need the main video running, and you will not need the load bar, all the recommendation, and the description, and also the comments. And just by giving to our system this purpose, we are able to watch YouTube. So it just showed that if we give a very good purpose, our prototype works pretty well. And like you can see, you can still see options and yeah, but you will not be able to do something else than watch this video, because this was the purpose that was given on the task. But the problem is that we did our study for a large number of websites, and it's quite hard to know when it's broken or not. For YouTube, it's quite easy, like you see the video running, you're like, yeah, it works. But how does it work for other pages? So for example, here for Airbnb, how can you say that the page is broken? Can you say just this because you see that it looks okay, I can probably browse it, but what happens if, for example, you cannot click on an element that you will need to check? So if you need to check, probably you will need what we call functional breakage. So this, I will tell about it later, but we just test that for a specific task, with our loading system, you can still perform it. And then we also have other questions like, should a human check it? So should we just run a big user study? So for now, we are not running one because our system is still in development, and also it's quite heavy and expensive to do it, and even more because we want to do like a test on a large amount of web pages. And so this is where we go. Can we automatize the check? And this is what we are doing. So we are running a visual breakage experiment. So just by checking one website next to the other. So for example, I took specifically one that's where we really see that there is a difference, because most of the time you don't really see it. But if you give a specific task, so search and compare where to stream specific movies, you will have two different images, and then we have an LLM that with the task and the two different images will say if it thinks it's achievable, so you can achieve the task on the actual web page. If it's difficult, not achievable, blocked, or inconclusive. And to be sure that this works, we run also an experiment on real user. This time we also give these two images and we ask them what they think about this. And this is just to double check that our LLM-based comparison of image is not doing crazy things. And what we notice is that humans often think that a web page, like a task, will still be achievable when the LLM thinks it's not. So humans are more optimistic than the LLM for that. And the second breakage we are measuring is functional breakage. So we design a variety of tasks. So this task can be on a normal website, also censored website. So we took the Citizen Lab censored list of URLs. And we create real tasks. So we ask, like we created ourselves. So the task can be quite simple. So for example, just go on this translation website and do a translation for flower in Spanish. And then like the answer of this should be like, okay, I have some translation in Spanish. And how we implemented it to make it automatic is like we give a task to a web agent. So the web agent will try to use it to make the task work. And then we know that the web agent needs to have some goal, so where it should land, for example, or what it should gather in the page as for information. And if the agent managed to do it 2 or 3 times, we consider it as the task is completed. And so this is how we do functional breakage. And now that we know how to evaluate our system, we'll have some results to show you. So on the visual breakage, we have 27% of the web page that are considered as broken by our system. And with the Tor safest mode, that is the baseline of the study, we see that the visual breakage was way higher. The functional breakage, so the one with the task, we have 11% of breakage, which is different. We cannot really compare, but compared to Tor safest mode, it's 3 times smaller for the same task. And in general, 56% of the resources are not loaded by our system. And and 86% of trackers domains are blocked. So it means that by design, by just loading what you need and not what you have to load, you will not load most of the trackers. So it goes very close to what ad blockers do. So ad blockers do 99%. And we also have 15% of resources that are blocked uniquely by MinBro. And this 15%, includes constant management services, new browser fingerprinting, and new trackers advertisers. So for this, we look them by hand to see what's going on, because they were not available on ad blockers. And on the website fingerprinting, what's happening? Because we are loading less packets, so we should have a real improvement in the website fingerprinting, because just making it smaller, you can think perhaps all the website will look alike. So yeah, so this is what we had before. So the big elephant is our website without defense, and if you compare it to everything around, it will really look different. However, what we notice is like using Tor plus our defense MinBro, it's still, you can still like know what's going on. And yeah, so it's like if I ask you to know in this page, where is the small elephant, you will still be able to know it. And there is a good reason for that, is that the index.html, so when you just load the index.html, it gives enough information to for the classifier to know which website you're browsing. So if you just have index.html, website fingerprinting works. So our system cannot work on top of it because we are loading index.html, whatever. But our defense is not meant to be used alone. It will work pretty well with other Tor defenses. So for example, here we are using in our experiments Tor plus front. So front is a state-of-the-art defense on the Tor ecosystem, and it will just mostly add packets at the start of the browsing session, because as we also noticed in the previous slide, index.html already contains a lot of information. So if you protect your traffic just by adding packets to the first part, you will probably hide the pattern. But with nowadays attacks, the Tor plus front result is quite high, so 0.83. So it's exactly as I saw in one of the previous slides. It's like if you want to hide a very big packet with an elephant on it, like it will still look different, and you will still be able to know which one the website was browsed. But something that's interesting is like when we add our defense on top of front, so MinBro, we have scores that decreases. And it goes very close to what we can have with just having front plus only the index.html. So when you just load index.html with front. And the reason of that is like if you make your traffic smaller, if you make your elephant smaller, and then like it would fit better in a packet that looks more like the others. But this is not just the good thing, these results. They are very good because they come with very nice overhead. So we have lower F1 score, and it comes with latency overhead that is reduced by 23% and bandwidth overhead by 44%. But how can it work? Because we saw earlier that the anonymity trilemma said we cannot have higher anonymity, so lower F1 score, lower bandwidth, and lower latency at the same time. And this is because, as I said, we come with breakage. And this breakage is a trade-off. If you want some part of the website to not work, but want also to have good anonymity at the same time, you can. And this will be a new axis, and the trilemma will be breakage. And yeah, so that's really the trade-off I was here to speak about today. And yeah, so there are a lot of challenge that comes with it. So this is more like I'm showing you the prototype, how it looks like. The goal is really to protect the subset of the page that the user cares about. And yeah, we are quite excited by the results, and we are planning to submit it soon to conferences. And that's it for me today. I want to thank my colleagues and co-authors, so Carmela, Simon, Alia, Harry, and Said, for these two work pieces I did the last year. And yeah, if you have any question, comment, I'm here to answer. Thank you. Yes.
I'm curious if you compared it against maybe an aggressive ad blocker. So, because I understand where you're coming from, like breaking the page,
Yeah.
but the ad blockers have worked hard to break the page less badly. And I would just be really curious how your system comparatively performs.
Yeah, no, sure. I have results, not here. But here, if you have ad blocks, it will be in between, it will be 0.69. So we are still like loading way less resources than AdBlock, because AdBlock is mostly to block ads. And nowadays also trackers, but still, like, for example, they will keep the page as it is most of the time. And yeah, so it will be in between, but still it's still a trade-off in a way. And we can also couple our defense with an ad blocker top of it. That's not really the goal now, because now everything we have is on the client side. So the client really decides, it doesn't have to trust any list. And yeah, but definitely, like, we are comparing it to ad blocks, and ad blocks still have lower defense compo when we couple them with Tor front, for example, here.
What else was that?
Yeah.
I'm surprised that the latency still goes down when you have an LLM
Yeah.
doing the filtering. How do you?
Yeah. Very good question. So when we have LLM, it just adds 20 to 50%, depending on the time on the total load time. Here, didn't go into details because I thought I would not have enough time. This is a specific implementation where you already went once on the web page, for example, and you want to go again. So it's kind of replayed. So it's with a list that you created. And if you will browse with this list now, it will go lower. So if you already know the resource you want or not, you just like cancel the LLM cost. And canceling the LLM cost makes the latency goes lower. But the bandwidth will stay more or less the same. Yeah.
So in the anonymity trilemma paper, the bandwidth is about bandwidth overhead. That means that's the demi traffic part of the whole thing. But in your paper, by breaking the web pages, you actually lower not only the bandwidth overhead, but the bandwidth itself, right? Yeah. And that gave me a question of, for example, if I am using a browser to browse a web page, does this behavior from the sender perspective different from this behavior that you introduce the MinBro and sending the request just to fetch a resource from API instead of fetching everything, just to use the browser?
Can you repeat the question?
Yeah, could using MinBro or could breaking the page itself cause more linkability from the sending behavior?
From the sending
behavior? Sorry, from the requesting.
So requesting here will be between I arrived somewhere probably. So where will be requesting here for you? This way?
For example, I'm having a browser. I send a GET request to fetch some resources,
yeah.
Right?
So Jollès makes
I need to first make that request, then I receive the response, right?
Yeah.
So normally when I get that index.html.
Yeah.
And while I send that get index.html, the server process all the things and send me not only the index.html, but also the icons, the images, the audios, the tracker, everything back, right?
Mm-hmm.
In your case, in your example, you give the example that we use the API instead of just send a normal like GET request. Will that behavior look different from the other users?
So it will, like, what you will do and what you will receive will be quite different from what someone will do usually. Like on the server side, it will look very different because indeed, like, you will do certain requests and not others. And that will make you unique in a way.
Yes.
Okay.
That's my point.
Yeah, yeah. And that's that's a problem because also now we are making things more unique because you have a website and one purpose.
Yes.
And the combination of two can be unique.
Yes. So if I am the service provider, I can say, oh, all the other users are requesting the HTML page. Well, there is one user who always requests.
Yeah, so that will happen here. So probably what you will be able to do is to say, oh, I think I received the same query by the same person twice. Okay, and the thing is like you still have this part. That's the thing that someone will be able to know that someone is here. So it can be like pseudonym, for example. You don't have the real name, but you know that's the same person.
Yes.
But we'll never be able to know that was Alice because of the anonymous communication network. Will never be. It's like you can, but
yes, I'm not doubting that part. What I mean is, even though I don't know your real identity, I know there is someone who is always requesting in a different way.
Yeah.
Thus I could link all this all these activities of requesting to one person, though I don't know it's Alice.
Yeah. And this will also depend then on the size of the user that use the system. Because if you have a lot of people using it, like the anonymity set will become bigger and bigger, and then like classification will be harder. But indeed, like if there are like 5 people using it in the world, like you will be fingerprintable on the server side, and perhaps will even be able to do like to know which person visits different website, because perhaps purpose will be the same and you can know. But it's a very good point. It's not on our threat model, but definitely something that can happen. Yeah.
Is it possible for adversary, let's say an adversary controls a portion of the internet and can also create websites. Is it possible for an adversary to create websites such that the defense becomes weaker? Or on the flip side, is it possible for an ally to create websites that are less distinguishable? Because you said index itself also reveals a lot about the website.
So good question. So if you want to make the attack weaker, you just have to randomize all your index.html, just make resources look random, and like no one can know what's happening. Because most of the time, like you can just say, okay, you need to load all these JavaScripts to make it work, and just make them having like random names, and that will just break the system. Hopefully it's not what's done nowadays. And if you want to make it our defense friendly, you can. And the best thing you can do, for example, is just to have simple web pages, because if you have just very simple index.html with that contains all the information, it's kind of a defense by default, because you will use it with front on top, so adding a lot of packets. If it's like just 4 or 5 packets you sent and you have 100 of them sending at the same time, we'll never be able to know what's happening. So yeah, you can make it friendly. You could also make kind of APIs. Nowadays, you have websites that have APIs that minimize the content that is requested. So it's mostly used for LLMs nowadays. Like, you can just ask an agent to book a flight, for example, and it will just call API of booking.com, for example. And this is already like data minimization, because you will just do specific requests with specific names, and you will receive exactly the content you need. But still, most of the internet is not like this. Yeah.
I guess following up on this question, if you had an adversary who was hosting the websites, who was also colluding and performing the fingerprinting, is there any possibility they might be able to prompt inject your LLM that is processing which resources it should further fetch? I mean, I guess in the worst case, it just forces you to fetch more resources that you would usually be fetching if you were browsing normally. But is there any chance they would be able to defeat your
I'm changing all my image names to ignore all previous instructions that day.
Exactly, right? Like,
yeah, no. Indeed, this is also why we are trying to extract the content of the index.html to just components that will be useful to link with the resource. Indeed, like should work. So perhaps we should add safeguards to it. But yeah, it's like always the thing with prompting attacks nowadays on LLMs, like you can find a way to evade them and then they find a way back to attack. Yes?
I feel like you've inadvertently opened yourself up to a new attacker. So I've worked before in consent dialogue blocking. So wow, is that a hostile space? Because legally the person delivering the consent dialogue has to have it there. And so there's a massive cat and mouse game to have them found automatically on the screen or not. And so on one hand, you're worrying about the attacker that's kind of trying to link the traffic and fingerprint it, but you kind of now have this secondary attacker that's really trying to make sure this content shows up. And one of the ways it's doing that is by actively changing the shape of the content on the page. And by this, I do not mean for tracking purposes necessarily, it's to explicitly avoid the blockers. So you look at like the ad blockers, and I would have an undergrad build something one year that just doesn't work the next year because the ad blockers have all updated. And this is partially tying back to the LLMs because the LLMs are being trained on the stuff we know now. And I'm really curious how resilient they actually are if you wait even a week to kind of that very hostile environment of advertising and consent dialogues and tracking.
Yeah, that's to be honest, it's really open question thing. Like advertisement, people will always find a way to make money. So probably like our thing works really well with advertisement because it's completely something new in a way. But perhaps they will be able to make it work differently. But still, like if the website does not collude with advertisement, people will still have like the components, how they look like in the page, and still you will see that this is most on the side of the page, so probably it's an advertisement, or like there is no real caption, so probably it's an advertisement. And you know, like you can build your own website nowadays. It's quite simple, and you can just say, okay, I want advertisement there. Yeah, so with that, still we will be able to evade, but indeed, like if advertisement companies want to make our system not work, as I said, they can just try to randomize everything, just try to put advertisement in components that are not meant to be advertised.
They do that.
They,
I'll just drop the other point.
Yeah.
There's 8 advertisements, so the option of getting the user to tell you not that this is a thing that should load, they're very open to it actually.
Yeah. If you're curious, I have here. So this is how we check with our humans, people, how it looks like when you use MinBro on the right and when you're not using on the left. And we have like, so this was what human had to do to know what's happening. And most of the time, like it's more about, it's more about like images that are loaded or not than advertisement. We didn't see a lot of advertisement up. We often have like the consent bars. We are in Europe, so we often have this. You have cookies, and they often not loaded. So that's quite nice. Yeah, some pages like still like here you can see WhatsApp icon is not loaded. You don't have consent. Yeah, you don't have photos. Yeah, so this is how it looks like, and so this is exactly the pages that we use. These are random pages that we used for our visual breakage study. Yeah. Other questions? Yes.
Using do you even need an LLM to do this? I could imagine you trying just like a text classifier or something.
Yeah, that's exactly what we do.
Okay.
So we do this, and then like since it's quite new thing to do, we still have to check with humans that we have similar results by doing this by LLMs or doing this by humans.
I know I mean the text classifier as like a machine learning model as well.
For the filter, you mean?
Yes, for the filter.
Yeah, that's exactly what we do also. We use LLM for the filter. Yeah, that's not the question.
Oh,
Do you mean you used an LLM that you got off the internet? That's one of our famous ones, or do you mean you hand built one locally?
Okay. So we are using both. For most of our experiments, we are using DeepSeek because it's quite cheap and fast. But we also did some experiments on local site, and we have similar results. But just that, it's models can vary a little bit, but we had like similar results in terms of F1 score and tracking system that were not loaded, and I think that's it. But we tried both. But indeed, like if you ship everything to an internet LLM, you kind of lose the advantage because now the LLM is the adversary.
Okay, we're out of time. Let's thank the speaker.